Greetings, everyone, and this is Mr. Mull, and in this podcast I'm going to be talking about the circuits and the differences between circuits that are series and that are parallel. So in series just means in a row, parallel means that there's multiple paths for charge to flow. So what I want you to do before we even get started, this is a PHET simulator, and here's a little bit about them and the copyrights and that kind of thing. The first one on the top right here, I have a circuit, and there's only one light bulb, and you can see how fast the charge is flowing in that relative to the other two circuits, and you can also notice how bright the bulb is flowing. Now the brightness is really related to the power output of the bulb, and that power depends upon the current, but also the voltage, and the resistance. So there's really a lot to play in the power. But you'll notice that there are some brightness differences. And because they're all the same resistance light bulb, that brightness difference is going to be related to the current and the voltage at each one of those light bulbs. So looking at my first circuit here, I've got one bulb in series with the battery, and I've got a certain flow. I can go ahead and put my little amp meter on here. Okay, we've got 0.9 amps of current, so 0.9 coulombs per second. Then I stuck two bulbs in a row. You'll notice the brightness dropped. And now I have two resistors, two obstacles for flow, and now I have, oh my goodness, 0.45 amps. And I look at all throughout the circuit, it looks like no matter where I look, it's 0.45 amps. Okay. Now the second circuit over here, I have, it looks like it's actually brighter bulbs. There's actually more current flowing in and out from the battery, and it looks like I've got 1.8 amps going in, and then very predictably, if I've got 0.9 amps going down this path, then the other path is the other half of the total current flow, 0.9 amps, and you can see that the current splits and then it rejoins back here, and then we get back to 1.8 amps again. Okay. Now what's interesting enough is if I change the resistance of this light bulb, let's say this is now a short circuit. Here, let's do that again. Whoa! Okay, I'm going to go ahead and make this a little bit less resistance. Okay. Now what I want you to notice now is that not only is the top bulb brighter, there's actually more flow in that path. I can see it. I've got 2.18 amps here. I've got 3.8 amps total, so messing with that resistance changed the overall resistance in the circuit. So now there's actually more current flowing. 0.9 down here, 2.18. So I add 0.9 and 2.18, we're going to get back to 3.08. So what we're noticing now is that more current is actually going down that path with least resistance. Okay, it's just like if I'm trying to go home, and I've got a path that's really kind of got a lot of traffic in there, a lot of traffic jam. It's going to be a slower path. More cars are going to be able to go down the path that's easier to get through. Okay, that's just how it works. It's just with cars, it's how it works with electrons flowing through the circuit. Okay, so a couple other things I want to point out here that are really kind of interesting is I'm going to look at my voltage of my battery here, on my series. Okay, we've got 9 volts, and then I'm going to go to my light bulb, and I'm going to see that at the light bulb, I'm going to do the red on, flip these here. Okay, we've got a negative 9 volts here, so 9 volts is energy per charge. The battery was giving 9 joules per coulomb of energy to the charge, and now it looks like this light bulb is taking away some of the energy and obviously turning it into heat or light. So it looks like all the 9 volts the battery gave it was lost at the light bulb. Okay, interestingly enough, I've got the same 9 volt light bulb. I go down here, and okay, I'm just kind of flipping these leads around. So I've got 0.45 volts coming from this light bulb, and another negative 0.45 volts coming from this light bulb. So what we're seeing is that 9 volts, if I've got two light bulbs in a series, each one is using up half of the energy, and then when it gets through that last light bulb, now it's back to 0 again, we start over. Okay, I'm going to formally define all this stuff, but I just want you to see that it's true. Now what's really weird about this last one is that right now, I've got two separate light bulbs with different resistances. So you're thinking, well, the voltage must be different. I mean, that change in energy across each of those paths. But very, very surprisingly, I want you to see it to believe it. I'm going to find the voltage difference across this bulb is 9 volts. It's not 4.5, it's actually 9 volts. I'm going to go down to this bulb here. The voltage potential difference across this bulb is 9 volts. And the voltage of the battery is also 9 volts. So for this circuit I've just drawn, that potential difference is actually the same on either side of kind of these pathway junctions. So we're going to talk about that in just a little bit. I just wanted you to see it to believe it. Okay, so we're going to do a little lesson on series and parallel circuits. What's going to correspond with this lesson is worksheet 3, 1 to 7, and we're in chapter 23 right now in our textbook. Okay, so let's talk about the series. We're going to kind of define and talk about some of the things that we noticed in the simulation. Okay, so something that's very characteristic of our series circuit is there's only one path for charge to flow. Okay, there was only one path for charge to flow. So I can go ahead and draw my little circuit here. So let's say I had two batteries in series with each other, and I have a little circuit here. And sorry about that. It's kind of a weird thing here. Okay. Let's say I have 2 resistors. Okay, resistors are typically just made with like a little squiggly line. Okay, that's the symbol for a resistor. Okay, so a little bit about the battery. So this end with the bigger line here, this is representing the positive end. This end with the little smaller line is representing the negative end. And this battery is providing some voltage. If this were like 2 3-volt batteries, you can kind of see them kind of stacked on top of each other. This might be like a 6-volt potential difference provided by the battery. And so we can have resistors in a row. Okay, we can have resistor 1, resistor 2, and there's only one path for charge to flow. So what we noticed in the simulation and on the virtual lab is that the current that was measured was the same at all points. Okay, so no matter where I look, where I stuck that little non-contact ammeter, now obviously a real ammeter we actually have to put in the circuit so the current can flow through it, but current is going to be the same at all points. So the current flowing through resistor 1 is equal to the current flowing through resistor 2, which is equal to the current that is flowing through the batteries. They're all the same exact current. Okay. You can only go as fast as the slowest car in a traffic jam. It's also like marbles in a garden hose. One goes in, one goes out. You can't go faster than that because electrons are just cruising along, and when I push one in, one gets pushed out the other side. That's what current is like. I'll just put on here, marbles in a hose, if that helps you. Okay, so parallel circuit, the difference is that we had multiple paths that charge could flow. Okay, so and on each one of those paths, we had to have one resistor per path. Whether that was an actual resistor or let's say per branch, or a light bulb is also a resistive element, or whatever. Okay. Okay, so I'm going to draw a little picture of what we saw there. So here is my, let's say I had 2 batteries stuck together, and I have, okay, so my current leaves, and then it gets to a place where it can go down 2 different branches. Okay, so it can go down and go through this first, let me draw a little squiggle here. It could go through this first little resistor, or current could go down the second little resistor. Okay, think of it as like 2 ways to get home. Okay, either way, you're leaving the battery and you're coming back to home if you're an electron. But if there's 2 different paths, call this resistor 1, resistor 2. If there's 2 different paths, then you've got multiple pathways that you can go. So what I did when I looked at that, and I looked at the current through each branch, what we noticed was that the junction rule was true. All the current flowing into a branch was equal to the current flowing out of that branch. So it all added up to the same amount of current that was going kind of through the battery. But you'll also notice that when I changed one branch, the other one's current may have also changed, but they were independent of each other. Like charge flow through one branch was just going regardless of charge flowing in the other branch. So current through a branch is independent of other branches. Okay. So this is kind of like cars in a traffic jam. The more traffic went down the least resistant path, and that least resistant path always had more traffic. It was kind of independent of what was going on in the other path at some moment in time. So what this looks like mathematically with the junction rule, the junction rule, is that when I added those two currents together, if I just got two paths that they can flow, then those currents always added up to the current that was being put out by the battery. Okay, so these are some things that are true for these different types of circuits regarding current. Okay, now one thing I wanted to point out before I kind of move on is I'm going to choose some different colors here, and I'm going to choose red and blue. So I'm going to say that red is the highest energy electrons have, or a charge has. So we leave the positive terminal of the battery. Now obviously electrons are flowing, and those are the ones, but in terms of energy, we're still defining current as the rate that positive charge would flow. So if positive charge were flowing, it would be really high energy when it left the battery. Okay, so here's my little current. I'm going along, and I notice I've got two paths to go, and then I can hit a resistor. Okay, so what I want to point out here is that, and I'm going to talk about this more in a second, is that when the charge has the highest energy, before it hits a resistor to lose any energy, I could go down two paths here. All electrons kind of on this side of the wire are all going to be kind of at the same energy because they haven't lost any yet, assuming the wire is ideal. We didn't lose any energy yet, so all of the electrons in either one of these paths on these points are going to have the same amount of energy. Okay. Now I also want to point out that when I come to the other side of the battery, I'm going to use blue here for low energy, that when an electron has gone through a circuit, when it gets back to the battery, it's going to lose all the energy it can. Okay, it's going to lose energy and it's going to dissipate, or it's going to try to get rid of as much energy as it can until it gets to the battery where it gets recharged and recycled. So I'm going to put the lowest energy next to the bottom end of the battery, and I'm going to connect that with all points in the circuit until I hit a resistor where I would have had caused me to lose that energy. Okay, so what I'm noticing as I draw this out is that there's really only two possible energy situations, the high and the low. And so when I look at going across both of these resistors, what we saw in the simulation was that the voltage change was exactly the same as the voltage in the battery. Okay, so if the voltage that the battery gave it was 9 volts of potential difference or energy per charge, then each one of those resistors had the exact same voltage but opposite as the current went through those branches, because to go from highest energy to lowest energy, you've got to lose and ditch all that energy. So each one of those resistors had the exact same voltage drop, and I saw that in the simulation, and that just meant that the potential difference across that resistor was, in fact, the same. However, when I go back and look at this first one here, the voltage was not the same at each resistor. So I'm going to start out again, and I'm going to get my highest energy. Okay, so charge is the direction that the charge is defined as the direction that positive charge would flow. So if my positive charge was flowing, before it hit a resistor, it would have its maximum energy, so I'm going to use red. Okay, until it hit a resistor to lose some energy. Okay, so I hit a resistor, and I'm going to get blue here, go to the bottom end of the battery. Okay, the lowest possible energy situation is when you get to the end of the circuit and you've gone through all the resistors. So I'm going to draw that until I hit a resistor. And then what we're going to find is there's kind of this middle point in between. So I'm going to use like yellow here. So what I saw was at the first resistor I lost like 0.45 or 4.5 volts. And then the second resistor I also lost 0.45 volts. But the battery itself was 9 volts. So what this shows is that as I was losing energy, I lost some at the first resistor, and then I still had to go to the second resistor, and then I lost some more energy, and then after I went through the entire circuit, I'm back to where I started again. Okay, so I just wanted to point out that the voltage drop was different at those different resistors where it was the same. And the color thing is just going to try to help us. So let's go to the next slide and kind of talk about what we just saw with the voltage. Give me 1 second while I get rid of this old lecture note piece. Okay, so let's talk about the voltage then. Some things that we noticed with the voltage for series and parallel. So in series, what happened to the voltage was the battery's voltage got split across the individual resistors. Okay, so what that looks like on my mathematical piece was that the change in voltage, I'm just going to put absolute value, the voltage, the potential difference of the first plus the potential difference of the second was always equal to what the battery was providing, the voltage potential difference of the battery. So, for example, I had 0.45 volts plus 0.45 volts equals the 9 volts to the battery. That voltage got split across the individual resistors because they were all in a row. Once the electrons lost energy, then in the next circuit they lost the rest of the energy, and that was all equal to what was available from the battery. So this is kind of that loop rule we talked about, where energy is definitely conserved. And so when I look at, and I'm going to come up with a little analogy in a second here, but what was going on was that each new resistor in series increases each new resistor in series increases the overall resistance of the circuit. In other words, the more resistors you add in a row, the more stoplights you add on your way home, the flow is going to decrease. Because overall I is decreasing. So because overall I was decreasing, as I added more resistors, the overall current was decreasing. That meant that each new resistor you added in series was increasing overall resistance of the circuit. So when I go and look at this circuit that I had going here a second ago, you'll notice that that the one that had multiple resistors in series, you can see the current flowing is less, and we saw that when I compared them. You've got more stoplights, you've got more obstacles, resistance goes up, therefore current goes down in your overall circuit. Okay, so mathematically, the equation is that the equivalent resistance, also known as the total resistance of the entire circuit, okay, the total resistance of the entire circuit, let me get back to my purple here. Is going to be equal to the resistors 1 plus resistor 2 plus resistor whatever. So what happens is, as you add resistors, you've got to go through more and more resistors. The total resistance is just going to be equal to the sum of each of those. Okay? On your equation sheet, what this looks like, they say that resistance of resistors in series is equal to the sum of the individual resistances of each individual resistor. Okay, that's what that is going to look like on your equation sheet. So when you see that, that's what you know what you have to do. When I look at the parallel circuit, what happened was the voltage, okay, that energy per charge, is this was the same across each branch. Okay, the voltage is going to be the same across each branch. So the voltage drop going at object 1 is equal to the voltage, the change of the potential difference at branch point 2, resistor 2, was equal to the voltage potential difference of the battery. Okay, when I look back at my thing here, I can see the colors. You see the colors are equal for each one of those because they had the same change in energy situation. Whereas in series, I lost a little more, I was at the bottom. So each one of those drops added up to the total, whereas here they were all equal to what the battery was providing. Now I've got a little analogy here, and I'm just going to draw a little slide here. So for that first problem, okay, I'm going to draw two little slides here. And I want you to tell me how these slides, maybe pause about it and think about it for a second, how these slides could represent the difference between a parallel circuit and two resistors in a parallel circuit or two resistors in a series circuit. Okay, so now that you've kind of thought about that for a second, the slide, or the, when I look at the slide and I go up the stairs, that is representing me gaining energy. So you can kind of think of it like, okay, potential energy, we're gaining energy. The battery is giving energy to the charge. So I get up on top of the slide, and every time I go down the slide, I'm losing some of that potential energy. So I've got, this might be delta V1, this might be delta V2, and those are going to always add up to, I get to the bottom of my slide, okay, then I got to go back over. So you can kind of think of resistors as being things that, use up energy or change the energy situation of your electrons in a circuit, and they're always going to have to add up back to what the battery gave it in the first place. When I have two separate paths, what happens is, as I get energy from the electrons get energy from the battery, what happens is I get to a possibility where now I've got multiple paths. I've got like a double slide. Not only can I get more kids going down slides because I've got two paths, each one of those slides is going to represent the same energy drop to get down to the bottom of the slide, the end of the circuit, and then go back again and start over and get recycled and re-energized. Okay. So this is kind of like an analogy, and when I use those little colors, I can think of like, okay, the top of my slide was the highest energy situation before I hit a resistor, and the bottom of the slide was my lowest energy situation when I got back to the battery, and there was only one way to do that. You just went from high to low, so that drop was the same for each branch of the circuit. Whereas over here, you've got those different little intermediate steps where I had my yellow, I lost it a little bit, but I still had some, and then at the top was my highest energy situation. Remember, voltage is energy per charge. So what does this look like for looking at kind of a little bit more about this? What was kind of interesting is when I looked at the simulation, the circuit that had the actual most amount of current flow was the one where I had two, I'll even make these the same light bulbs, or the same resistance. The one that had the most was actually the circuit that had flowing the fastest. Now I'm slowing down my computer, but the one on the left is still the fastest current, and the bulbs are the brightest. How could that be? How could more current be flowing through that first circuit? And if you think about like trying to get from your house, school to your house, and let's say everyone in the school is going to your house or something, if there's more ways to get there, there's going to be more flow to your house because there's more paths to go down. Even if I've got a resistor there, it doesn't matter. So I'm going to put on here each new resistor in parallel let me get back to oops, here we are. Okay, each new resistor in parallel is going to decreases overall resistance in the entire circuit. And the reason why that is that's because the total total current increases with more pathways. So I have more paths for current to flow, more can flow. Okay. So the mathematics of this, and I'm not going to drive how we come up with this equation. It could be done. But at the end of the day, what happens is if we take the reciprocal of the total resistance in the circuit, it's going to be equal to the sum of the reciprocals of each individual resistance of each resistor. So I can use I can hit all these with a -1. So in other words, the equivalent resistance is equal to all those reciprocals added together, to the -1. That's one way we can find that equivalent resistance. When I look at my equation sheet, what I'm going to be looking at is this. 1 over Rp stands for parallel, is equal to the sum of the individual reciprocals of each individual resistor. Okay, so that's what I'm looking at in my equation sheet. So I'm going to do a quick example with this, so you can kind of see it in action. Okay, so this is example number 8 from our little handout. So we're going to do a problem where we have 3 resistors connected together in parallel and then connected to a 9-volt battery. So I would draw this out, and if they're connected in parallel, I'm going to have multiple branches. So there's many ways to draw this, but essentially I've got a battery, okay, and this battery is providing 9 volts of potential difference, and essentially what this means, however I draw this, is I've got to have 3 paths before I hit a resistor. Okay, so there's many ways, again, to draw this, but I'm going to go ahead and draw 3 ways, 3 paths to go when I leave my battery before I hit a resistor. And then those 3 paths are going to have to meet back up to get to my final battery. Okay, so it says that I have a 4 ohm resistor, I've got a 7 ohm resistor, and I've got a 10 ohm resistor. Okay, so here's kind of the situation. Now what I would probably do right now, just because it kind of helped me, is I'm trying to figure out, as I'm drawing the circuit, now this is an easy one because they're all in parallel, but I'm going to do it anyway. I'm trying to think of, how is voltage changing across each resistor. So I'm going to start with my highest potential difference and go until I hit resistors. Okay, remember all of these are going to be on the same energy situation because they're all representing electrons in the wire that had the same energy before any was taken away through a resistor. So all that will be red, and then I'm going to go to the bottom end of the battery when electrons are going back, or when charge is going back to the other end of the terminal, and it's going to have used up all of its energy. I'm going to go ahead and draw that blue. Now when I draw this, there's no leftover intermediate voltage drops. That means that each one of these resistors is getting the same exact voltage drop, the 9 volts total. So it says find the equivalent resistance of the group and then the current flowing from the battery. Okay, so if I want to find the equivalent resistance, that's the total resistance coming from all the resistors together. So to do that, I can take the sum of the, so I look at my little equation sheet, we're in parallel, the sum of the individual resistances. Okay, so I'm going to add up all of the equivalent resistance in this parallel circuit, the sum of the individual resistors. So 1 over 4 plus 1 over 7 plus 1 over 10. Okay, they're all in parallel, so I can just add them together like shown. And then when I do that, I'm going to get that sum is equal to 0.493. But that's the reciprocal of the resistance. So to find the actual equivalent resistance, I'm going to take the reciprocal, in other words, 1 divided by 0. Or you can raise it to the negative first power, 493. And that's going to give me the equivalent resistance. Okay, so when I do that, I'm going to get 2.03 ohms. It's going to be my equivalent resistance. It makes sense that it's a low number because as I add more paths, resistance goes down. More paths to go, resistance should be going down, and it is going down. Okay, then the question says, find the current flowing from the battery. Okay, so to find the current flowing from the battery is pumping out electrons through all these paths. I want to find the total current going through the entire battery. So to find the total current, I have to look at the voltage total, the total amount of voltage, pushing power from the battery, and I have to divide that by the overall or total equivalent resistance of the entire circuit as a whole. All of the resistance the circuit is able to provide. Okay, so to find that total current coming from the battery. So if I take my 9 volts and I divide it by the resistance I just calculated, the overall resistance of the circuit, I can find the current, and it's going to be 4.4 amps. So now I know the current through the entire circuit. The next question says, find the voltage across and current through just the 7 ohm resistor. So now I'm going to look at just this resistor, and remember, we said that in parallel, the current through each branch is independent. That means that that 7 ohm resistor is getting its own little slice of that 4.4 amps. It's not getting all of it because some of that 4.4 amps is going through the other paths. So to find the current, we're going to have to do a little bit of work, but the voltage is easy for parallel circuits. Why is that? Well, look at the color coding I've drawn. If all my resistors are in parallel, each one of those resistors gets the identical voltage drop as it goes from one end of the battery to the other. So easy for parallel circuits, the voltage at the 7 ohm resistor is 9 volts. Okay, it is 9 volts. Okay, so to find the current at the 7 ohm resistor, I'm going to take the voltage across the 7 ohm resistor, because I'm using Ohm's law here, just like I used a second ago. Ohm's law is going to find me that current, divided by the resistance, but I'm talking about just the resistance to flow in that branch where the 7 ohm resistor is, up here. So if that's the case, I can find my voltage, I can find my current by taking the 9 volts divided by the resistance at that place, which is 7 ohms, and I'm going to get that only 1.3 amps of current is going to be going through that branch. Now you could do this for the other branches, and you can find out how that 4.4 gets sliced between the 3. Okay, let's do another example. This is example number 9 in our handout. So this one says 3 resistors, 4 ohm, 7 ohm, and 10 ohm are connected together in series in a row, and then connected to a 9 volt battery. So I would draw a picture first off. So here's my little battery. We've got 9 volts. There's my positive end, there's my negative end. Okay, I'm going to draw 3 resistors in series. Okay, there they are. And so I've got a 4 ohm, a 7 ohm, and a 9 ohm, and then I'm trying to figure out what they're going to be. So find the equivalent resistance of the group and then the current flowing from the battery. I look at my equation sheet talking about series, and I know that the sum of the individual resistors is going to be equal to the overall resistance. As more resistors are put in the row, the resistance goes up. So my equivalent resistance, or my total resistance, is going to be equal to 4 plus 7 plus 10. We're looking at 21 ohms of overall resistance in this circuit. So the second question says find the current flowing from the battery. Okay, from the battery means the total going in and out. So to find the total going in and out, I need to know the total voltage provided in the circuit, across the circuit, and I need to know the total resistance or opposition to flow in the circuit. Okay, well, I know that the voltage provided by the battery, the total voltage is 9 volts, and I know that the total resistance we just calculated with all 3 resistors in a row is 21 ohms. So much less current is going to be flowing through this circuit than would be if they weren't stuck in a row, because you've got 3 obstacles in a row. So it's like 3 little stoplights, and the total current is going to be equal to 0.43 amps. All right, the next question says find the voltage across and current through just the 7 ohm resistor. Okay, now this is going to be different. Now before I get into the voltage part, I want to talk about why is current easy for series. Why is this easy for series? So pause about that and think about that for a second as I'm writing this. Okay. Hopefully you were able to realize that because there's only one path for charge to flow, everyone's going the same speed. So the current going through 7 is going to be equal to the total current of the battery, which we already determined was 0.43 amps. So once I know that, my current's done. Now I want to find the voltage. And voltage is not the same across each one of these. Okay, so I go back and I say, okay, how does energy get used in this circuit? Well, I start with the highest energy. I lose a little at resistor A, and then I have some energy still left over. I lose a little more, and then I get to the 7 ohm resistor, and I lose a little bit more energy. Let me go green. Okay. Then I go up here, and now I've 7 ohm resistor. I lose a little energy there. And then I get past the 9 ohm resistor, I lose pretty much all I have left. And then when we get to the end of the circuit, there's no more resistance. My electrons have used all the energy. Now they're back to this beginning. And so I've got these voltage drops that are different at each one of these resistors. Obviously, they add up to 9 volts because energy is conserved. But I don't know which drop is at each place. So in order to figure that out, I can say, well, let's use Ohm's law for just 7 ohm resistor. And I want to find the voltage across that 7 ohm resistor. Well, thankfully, I know the current going through it, and I also know the resistance. So I can solve for my unknown voltage drop at that specific location in the circuit. So I take delta V is equal to I7 times R7, the current and the resistance at just that point. And I already determined that through the entire circuit, the 0.43 amps is flowing, and the resistance at just that resistor was 7 ohms. So there must be a 3 volt drop at that resistor in order to have that much current. And I could go back and do this for the 4 ohm and the 9 ohm, and you better bet that all those voltage potential differences would add up to the 9 volts of the battery. Okay. All right, this has been an intro podcast on series and parallel circuits, and what I recommend you do is try to work through multiple choice questions 16 through 18. Oh, I got one more part of the lesson, I'm sorry. This is just kind of a last little bit here. Which bulb won't light and why? Okay, so basically what I want to do is I'm going to start coloring, and I'm going to use an explanation for that point. Okay, so here is my highest energy situation. Until I hit a resistor and lose energy, I'm going to all be at that same potential difference. Okay, so there we are at the top of the slide. Then I hit a resistor. Before I get to the next part, I'm going to go to the bottom end of the slide and draw the lowest energy situation until I hit resistors. And what we're going to find is that this bottom bulb is actually going to be stuck in all of that kind of lowest potential energy situation, lowest potential difference. And only the first 2 bulbs are going to have a drop or a change in voltage, because that other bulb is kind of on both sides, all those electrons in that wire. This bulb, which bulb won't light and why? This bulb is definitely not going to light because there's no potential difference across the bulb. If there's no potential difference across the bulb, there's no reason for electrons to flow through it. Electrons are not going to be forced to flow through it because all the electrons on either side of that bulb are at the same energy situation, and we're always trying to go from high energy to low energy. So that's what an electron is going to do. It's not going to do anything. So if you're an electron, once you get through this bulb, your easiest path home is most certainly to go right to the other end of the battery. You're not going to force your way through another bulb. Same thing here. these electrons are going to flow through and they're going to go right to the other end of the battery because they're not going to be forced through that light bulb because there's no reason to. All the electrons over there are in the same energy situation. So if there's no potential difference across the bulb, it will not light, current will not flow through it at all. All right, I would try to check multiple choice questions 16 through 18 at the closure of this lesson. Read through the answers into the multiple choice practice and make sure you can do those. I hope that this has been helpful. Thanks for watching.